everyone, welcome to the second part of the 18th lecture in the series Mathematical Methods for Economics. In the first segment of this lecture, we talked about the various rules for computing limits. We sort of built up a toolkit for calculating limits algebraically. And because the focus of the discussion in this lecture is the exceptions to these rules, so we've started talking about the first set of exceptions to the rules. And this was a case when both functions f and g tend to infinity as x tends to a. So let us continue from there. And to summarize what I had just been talking about in the first segment, if both the functions f and g tend to infinity as x tends to a, then we can say that the limit of the sum will also tend to infinity, and will be infinity, because if we are making both f and g arbitrarily large, infinitely large as x tends to a, then f plus g will also become infinitely large. The same is also true when we look at the product of the two functions and we take the limit as x tends to a for the product of two functions, because both f and g tend to infinity as x tends to a. Therefore, the limit of the product will also be infinity. The problem actually happens when we look at, this third one should be a minus in between. So the problem comes up when we look at the limit of the difference of two functions, f and g, or we look at the limit of f of x divided by g of x, because the result in these two cases will depend on how fast the functions f and g move relative to each other, and how fast they shoot off to infinity relative to each other. That will then determine the result. Now, to illustrate, I have taken this example from the textbook Sitzeder and Hammond. This is a classic example which drives home the point that we just made very clearly. And in this particular example, we have f of x equal to 1 divided by x squared, and the function g of x is 1 divided by x to the power 4. Now you can clearly see that as x tends to 0, so a is equal to 0 here, as x tends to 0, both these functions, each one of these functions shoots off to infinity, right? Now the question asks you to investigate the limit as x tends to 0 of f of x minus g of x. So as we just talked about things in the previous slide, there will be no problem with respect to f of x plus g of x or f times g. The problem occurs when we're talking of the difference between the two functions or the ratio of these two functions. So if I look at f of x minus g of x, and I take the limit as x tends to 0, but let us first look at the difference. So f of x is 1 by x squared and g of x is 1 by x to the power 4. So when I take the difference, the LCM here is x to the power 4. So that gives us x squared minus 1 in the numerator. And you can see here that this is a situation where the rule that we had built up for the limit of the ratio of two polynomials for a rational function, here your denominator is going off to it is becoming 0, because x is tending to 0, so the denominator will also become 0. And because in the numerator you have a negative sign in front of 1, therefore this entire expression will tend to minus infinity as x tends to 0, right? Let me show you the theorem that we had talked about in the previous lecture. This says that if you have the rational function p of x divided by q of x, where p of x and q of x are polynomials, then as long as the denominator is not equal to 0 at a, you're fine. So the limit of the function is equal to f of a as x tends to a. But if the denominator at a is 0, but the numerator is not 0, which is what which is the kind of situation we are facing here, because the denominator was x to the power 4, and the numerator here is x squared minus 1. So numerator clearly is not 0 at x equal to 0. Then the limit does not exist, right? The limit may be the function, the expression might be going to minus infinity or plus infinity, or minus infinity from one side or plus infinity from the other. The point is this expression will tend to minus infinity. Now just give it some thought, because when I teach this part, some students, they take a while to understand why it's going to minus infinity. Look at this difference here, 1 by x squared minus 1 by x to the power 4. Actually, this very intuitively explains the result, because if you are, first of all, it does not matter, you can see here, because it's an even exponent. So whether you approach 0 from the left or from the right, it's going to be squared, or it's going to be raised to the power 4 in the denominator, so it's not an issue. However, you can see here that x to the power 4, as you approach 0, either from the left or the right, will be a smaller number as compared to x squared. So because of this, this 1 by x to the power 4 will shoot off to infinity much faster than 1 by x squared. And because of that, logically speaking also, you can see that, I mean, here we were just using the theorem, but logically also intuitive, this result is quite intuitive, because this second expression will shoot off to infinity faster as x tends to 0 as compared to the first expression 1 by x squared. And that is why the net result would be minus infinity as x tends to 0. Now, look at the second part to this question. This is asking you to investigate the limit of g of x minus f of x now as x tends to 0, and that is then going to be 1 by x to the power 4 minus 1 by x squared. Now here again, if I just simplify this expression, I'm going to get 1 minus x squared divided by x to the power 4, which then tends to infinity as x tends to 0. Because here also, now because 1 by x to the power 4 is coming up front, and x to the power 4 will be for any x, for any given value of x to the power 4 will be a smaller number. So 1 by x to the power 4 will tend to infinity much faster than 1 by x squared, which then gives you the net result as infinity. The next part looks at the ratio f of x divided by g of x, and this then is 1 by x squared divided by 1 by x to the power 4. So this then will give you, because when you cancel out the terms, you will get x squared here, if I would guess, because x to the power 4 will come to the numerator. Yes, so it's x squared, and that clearly tends to 0 as x tends to 0. Now what happens to the limit of g of x divided by f of x as x tends to 0? You can see here that g of x is 1 by x to the power 4, f of x is 1 by x squared. So when you divide the first by the second, then by g by f, when you take, you get 1 by x squared, and that clearly, because x is tending to 0, 1 by x squared will tend to infinity. So you see the variety of results that you get, and also you can work with some different functions on your own and see whether you can get some different results. So for example, I can ask you, will you always get, so for example, let me go back to this particular slide. If I'm looking at f of x minus g of x, so if both functions are tending to infinity, is it necessary that the result that you'll get will either be an infinity or a minus infinity? Think about it. So for example, you could think of f of x as the function, let's say 7 plus 1 by x squared, okay? And you could think of the function g of x as, let's say, 5 plus 1 by x squared. I've changed the two functions now. So the first one is 7 plus 1 by x squared, and the second is 5 plus 1 by x squared. Take the difference and see what you'll get. So construct different examples on your own and see what kinds of results you get. Similarly, see what you'll get for other kinds of functions involving f of x and g of x going off to infinity, and when you take the ratio, see what results you get. So that is a do-it-yourself exercise. Now let us now move to the exceptions, the second set of exceptions to the rules. And this is basically asking the question, let us have a situation where, let's suppose g of x, the function g of x tends to 0 as x tends to a. Okay. So, of the two functions f and g, g of x tends to 0 as x tends to a. The question here is, will the product of the two functions f of x times g of x also tend to 0? And the answer is, if you think about it a little bit, the answer is not necessarily, and especially not if f of x shoots off to plus or minus infinity. Okay, and let us take an example to illustrate this. Let us suppose f of x is given by 1 by x, okay, and g of x is given by x itself. So clearly you can see, and let's take the limit as x tends to 0 from the left. I've taken a one-sided limit here because you have a 1 by x. So if let's say x tends to 0 from the left, clearly you can see g of x will also tend to 0. So that assumption is fulfilled here, that g of x tends to 0 as x tends to 0 from the left. Now what happens to the limit? The question we were asking is, will the limit of f of x times g of x also be 0? Just because g of x is 0, you generally think that anything multiplied by 0 is a 0. And look here, look at what happens. When you take the product of the functions f and g, what do you get? 1 by x times x. And the x's will very nicely cancel out. And what do you get? You straight away get a 1. Okay, so clearly if, and here this was a situation where you can see here that the function f of x is one where as x tends to 0 from the left, you can think of the graph of 1 by x, as x tends to 0 from the left, this function will tend to minus infinity, right? And that then totally does not fall in place with the rules, the generic rules that we had set up. So this is another exception to the rule. The third set of exceptions, again this is something very simple. So it just poses a question that suppose the two functions f and g, each one of these functions does not tend to a limit. So here you have a situation that the functions themselves don't tend to a limit, but can you have f of x plus g of x tend to a limit? And what about f of x divided by g of x? So if you have a situation like this, let's take an example to illustrate. So let f of x be equal to 1 plus 5 by x, right? And let g of x be equal to 7 minus 5 by x. So what will happen? When you take the sum of the two functions, f of x plus g of x, the 5 by x terms, they get cancelled straight away. Now you can see here very clearly, f of x and g of x don't have a limit, right? And this is when we are considering x tends to 0, let's say. So here there is no limit. But for f of x plus g of x, we do have a limit. The sum tends to 8 as x tends to 0. Similarly, if I take the ratio f divided by g, that's going to be equal to x plus 5 divided by 7x minus 5, and that you can see clearly tends to, if I get x to go to 0, then this will tend to minus 1. Okay, so this is also something you should take note of, these kinds of situations, that individually f and g may not tend to a limit, but f plus g can tend to a limit. Okay, now what we'll do in the time that is left, I'll go over some practice problems which will quickly walk you through the various rules that we have developed. Now this one, as you can see, it asks you to calculate the limit of 2x minus 3 the whole squared plus 7, and this is, you can see it's a polynomial. Either you can just open up the brackets and get 4 times, you can just plug in the values, x, because x is tending to 1. So you'll get 1 minus 3, which is minus 2, plus 4, which is 2, and then because you have a 4 outside, you'll get an 8. Okay. Alternatively, you can use the property that the limit of the sum is the sum of the limits. So I've separated out limit of 2x minus 3 the whole squared plus limit of 7, and here you can see that the limit of 2x minus 3 the whole squared, you can apply the theorem relating to polynomials. You just have to plug in the value 1 here, and that will give you 2 minus 3, which is minus 1 the whole squared, that is 1 plus 7, that's the same answer as we got the other way. Let's look at the second example. This illustrates the rule. So x tends to 2 here, and this illustrates the rule where both the numerator and denominator are non-zero at 2. So there is no problem. We can just take the limit of the function here as the limit of the ratio as the ratio of the limits. So that will be limit of 5x cubed minus 1 as x tends to 2 divided by the limit of x plus 1 as x tends to 2, and that's going to be 5 times 8, which is 40 minus 1, 39 divided by 3, and that's going to be 30. Okay, this example, example 3, is one where you, when you see, look here, you have a situation where the denominator tends to 0 as x approaches minus 1, and the numerator also tends to 0 as x approaches minus 1. So this actually, if you think of this function, it at minus 1 it collapses to this 0 by 0 form, and because the numerator and denominator both tend to 0 as x tends to minus 1, you have what we call an indeterminate form, 0 by 0. So in this situation, these kinds of situations are conveniently handled through what is known as the L'Hopital's rule, but we'll be doing that in another lecture. There are 7 indeterminate forms which are typically talked about in the literature, but we will cover those in a later lecture. And if you look at how to handle, so we don't, the point here is we don't have to depend on L'Hopital's rule here. We can actually manipulate this expression, and you can see here from your basic algebra that x cubed plus 1 can be written as x plus 1 times x squared minus x plus 1 divided by x plus 1. The x plus 1 terms in the numerator and denominator get cancelled, and once you substitute minus 1 into this expression, you're going to get a 3. Let's look at the next example, and that is actually a very important limit. So if you look at limit x to the power n minus a to the power n divided by x minus a, where n is a natural number. Now the way I can calculate this limit is I can make things a little more systematic, just simplify things a little bit. Let's put x equal to a plus h. Okay, so clearly if x tends to a, then h will tend to 0, and this then gives me the limit of x to the power n minus a to the power n divided by x minus a is the limit of a plus h to the power n minus a to the power n divided by h, because once you substitute for x, the a's will get cancelled in the denominator and you'll have 1 by h. Okay, now you can use a binomial formula to expand for a plus h to the power n, which then gives me a to the power n plus nc1 a to the power n minus 1 times h plus nc2 a to the power n minus 2 h squared, and so on till higher powers of h until you reach h to the power n, and from there you subtract off this last term, which is a to the power n. And you can clearly see that the a to the power n terms will get cancelled here. So you're left with all these terms which contain an h. Okay. Now if I take h common in this expression in brackets here, the h will get cancelled in both the numerator and the denominator. And inside the brackets you'll be left with nc1 a to the power n minus 1 plus all these terms which actually contain an h. And this, obviously, when you apply the limit, all these terms, so this is actually a very clever strategy, because all these terms after n times a to the power n minus 1 will just vanish, and your limit then is n times a to the power n minus 1. So look here, so this is actually, if you have done differential calculus, you will recognize this as the derivative of the function x to the power n, at the point A. So if your function was x to the power n, then the derivative of the function at A is n times A to the power n minus 1. But for now, we have just developed this result for the case where n is a natural number. In fact, on your own, you could also apply this result to the case where n is a negative integer, because you could then just take a plus h to the power minus n here and use the binomial formula accordingly, and you will get the result. But for n being any real number, we'll talk about that when we actually do calculus, and we'll set up the result. Okay, so I have these other very simple problems which you can practice on your own. I'm just sliding through this presentation. You can look at these problems on your own. Limit of x plus mod x divided by x as x tends to 0 from the left, or limit of x plus mod x divided by x as x tends to 0 from the right. You can practice these problems on your own. This is also a very simple problem from Anton. You can look at this and try this on your own. So these are, I'm just going through these slides so that you can cross-check your answers. And then we will be looking at limits at infinity, but since we've totally run out of time, so I will sign off for now. And there'll be more problems, plenty of more problems coming for the other lectures on limits. We'll be covering limits at infinity. We'll be talking about asymptotes, the precise mathematical definition of a limit, and we'll also be covering indeterminate forms. So there's lots more to cover, and more to come in the next lecture. Okay, thanks.